Good morning, everyone. I'm going to now discuss in detail about adrenergic agonist or sympathomimetic agents. These are also called as sympathomimetic agents because they are going to act on the sympathetic nervous system, which normally which will be stimulated by the biological catecholamines that are epinephrine or adrenaline and norepinephrine or noradrenaline. So we have here some of the drugs which act directly on the sympathetic nervous system by activating the adrenergic receptors, so-called alpha and beta adrenergic receptors. And some sympathomimetic agents, they are going to act indirectly by increasing the production of norepinephrine and epinephrine, so that when the levels of norepinephrine and epinephrine increases, that will indirectly increase the sympathomimetic action based on the mechanism of action. That means based on how this particular sympathomimetic agents are going to bind at the receptors, they have been classified into directly and indirectly acting sympathomimetics. That means directly acting sympathomimetics are nothing but they are directly going and binding at the adrenergic receptors, which are classified into alpha and beta, and again alpha 1 and alpha 2, as well as beta receptors beta 1 and beta 2. Based on the site of receptor to which the sympathomimetic agents have been binded, there will be execution of related activity. When it comes to indirectly acting, they won't bind at the receptors, but by increasing the activity of enzymes that involves in the biosynthesis of catecholamines, they are going to increase the levels of norepinephrine and epinephrine. So moving on to the classification, as I have mentioned earlier, they have been classified into two types, that is directly acting and indirectly acting. First, we are going to discuss about directly acting sympathomimetics, which have been again classified based on the chemical entity which is present in it. So first subclass of compounds is phenethylamines and their related compounds. Under that, this phenethylamines again classified into two classes, that is catecholamines and non-catecholamines. Under catecholamines, we can see natural as well as synthetic agents. Natural agents such as adrenaline, noradrenaline, and coming to and dopamine, and then moving on to synthetic catecholamines called dobutamine and isoproterenol, out of which isoproterenol, which is also called as isoprenolone, is considered to be prototype of catecholamines under directly acting sympathomimetics. If we observe the structures, each and every compound of this consists of a catechol ring system followed by an ethyl chain and then an amine group. Amine group may be substituted or unsubstituted. Okay, regarding this we'll discuss in detail in the SAR of these compounds. And under phenylethylamines and their related compounds, now we have seen catecholamines. Moving on to non-catecholamines, that means these structures, they'll devoid of catechol ring, but still they consist of a phenyl ring and an ethyl chain and then an amine group. Okay, so here we can observe examples like terbutaline, salbutamol and bitalterol. So if you take terbutaline, it consists of a tertiary butyl group, and salbutamol, the catechol ring, it is modified by replacement of OH with methyl or hydroxymethyl group, and bitalterol, it consists of an ester replacement of hydrogen. So like this we have some non-catecholamines under phenethylamine derivatives. And moving on to next category of directly acting sympathomimetics, that is imidazoline derivatives. Under imidazoline derivatives, we have four examples here, that is xylometazoline, oxymetazoline, nafazoline and clonidine. So if you observe, each and every structure of this consists of an imidazole ring. Imidazole is nothing but a 5-membered ring compound which consists of 2 nitrogens at 1 and 3 positions. And if we observe carefully, there is presence of amine group in case of xylometazoline, and oxametazoline, a tertiary amine group will be present in the form of imidazoline rings, but not simple primary amines. Okay, here clonidine actually it is alpha 2 partial agonist, but that means it is going to act at the alpha 2 receptors, but because it is having direct action on the alpha 2 receptors, it is considered under direct acting sympathomimetics. Moving on to the second category, that is indirectly acting sympathomimetics. Here we can see examples such as hydroxyamphetamine, pseudoepinephrine, and propylhexitrin. So in this, here we can find a phenyl ring and an ethylene bridge as well as amine as in case of directly acting, but it is devoid of catechol ring system. And moreover, if we observe carefully, there is substitutions on the ethylene chain, especially alpha substitution, alpha methyl substitution, and in case of pseudoephedrine we can find a beta hydroxy group. Because of this alpha methyl substitution, they'll have an indirect acting effect at the sympathetic receptors, that is adrenergic receptors. Okay, apart from this directly acting and indirectly acting, we have some mixed acting sympathomimetics. Under that, which example is metaraminol. See, mixed acting sympathomimetics means nothing but they may act directly or indirectly, and they may have its action at both alpha as well as beta receptors. Okay, that's why they are classified into mixed acting sympathomimetics. Even here we can have one more example, that is ephedrine, which has a similar structure with the pseudoephedrine. They'll differ only stereochemically. That means because of substitution of methyl group on alpha carbon of ethylene bridge, there arises a chiral carbon which is giving us ephedrine structure, okay, which acts as a mixed acting sympathomimetic. This is in brief about classification of sympathomimetics. Now in next segment we will move on to SAR of sympathomimetics. So before going into SAR, we have to first understand the basic structure of sympathomimetics. As we have seen in the previous structures, there will be presence of a phenyl ring and an ethylene bridge, and then an amine group in the side chain. That means here briefly we can tell that the phenyl moiety and the amine is bridged by an ethylene chain. So coming to substitutions, here if you look into where actually the substitutions have to be carried out, the major positions here we can look into are the substitution on the phenyl ring at 3rd and 4th position, and then on 7th and 8th positions of the ethyl side chain, and of course on the amine nitrogen. So all these position substitutions are required, and the substitutions at these positions are going to influence not only mechanism of the sympathomimetics but also on their receptor selectivity. That means at which receptor they are going to bind. That means the drugs based on the substitutions, we can expect the receptor selectivity like alpha 1, alpha 2, beta 1 and beta 2. So next, moving on to modifications. As we have just seen, the 3rd and 4th positions on the phenyl ring are more important at the substitutions. So when this 3rd and 4th positions are both are substituted with hydroxyl groups, we'll get the catechol moiety, as we have seen in most of the directly acting sympathomimetics. Here that's why we can consider catechol moiety as an important structural features to get not only the maximum agonistic activity but also selective adrenergic activity. So here isoproterenol, which is non-selective when it is when the hydroxyl group is replaced from 3rd to 4th to 5th position, it gives a beta 2 selective agonist, which is nothing but metaproterenol. Like this we can go on modifications on the catechol ring. So the same point here we can discuss in another way, that is when this 3,4 dihydroxy compounds have been changed to 3,5 compounds, they'll resist to COMT metabolism. COMT is nothing but an enzyme which can be abbreviated as catecholamine O methyl transferase, which converts this catechol rings into their metabolites, active metabolites, so that they can be eliminated. So when this particular dihydroxy group, which is present at 3 and 4th position, is changed to 3 and 5, we can inhibit that metabolism, and there will we can increase the activity of sympathomimetics. Example for such compound is metaproterenol, where we can see hydroxyl groups at 3rd and 5th positions. Okay, these are brief modifications we can see on the phenyl ring. And then moving on to the amino group at position 9, which is essential for the direct agonistic activity, and we find that it is separated from the phenyl ring with 2 carbons, so that we'll get the direct acting agonist. And looking into substitutions, the kind of substitutions that are present on the nitrogen, so if we go on increasing the bulkiness, that means the alkyl group from methyl to ethyl, ethyl to propyl, what happens here? Alpha activity will decreases and beta activity will increases. That we can see in the form of when we take compounds also, we can see the order, that is at alpha receptors noradrenaline exhibit most maximum activity than adrenaline, and when compared with the isoproterenol. Why? Because noradrenaline is a primary amine, NH2 is present, adrenaline it is methylamine, NHCH3 will be there, and in case of isoproterenol it is isopropyl group. So clearly it is giving a clear it is indicating that when the methyl group or the alkyl substitution on the nitrogen is less, it is having more alpha activity, and if the alpha substitution, if the nitrogen substitution with more large alkyl groups, it is having less activity. In the same way, beta activity we can predict as isoproterenol is having higher beta activity than adrenaline and then noradrenaline. Okay, and moving on to next, so what the substitutions on, to what extent we can substitute on this nitrogen. So primary and secondary amines are more potent direct acting agonist than the tertiary and quaternary amines. Okay, and moving on to the methyl and ethyl substitutions on the 8th position. That means we are discussing about the ethylene bridge, which is present in between phenyl and amine. So on this ethylene bridge at the 8th position, that means alpha to amine group, on alpha position we can substitute methyl groups, so that we'll get an indirect acting sympathomimetics, so that it reduces the direct receptor agonistic activity. For this we can quote an example, that is hydroxyamphetamine, where we can observe an alpha methyl substitution. Okay, and moreover, when alpha methyl substitutions are there, these compounds they'll increase resistance towards MAO, that is monoamine oxidase enzyme, so that we can decrease its metabolism and increase the duration of action. For this we can take example, that is ephedrine, which comes under a mixed acting sympathomimetics. With this, these are the references which I have quoted. Thank you.